All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Maegan Tucker, who is an assistant professor at Georgia Tech, where she's jointly appointed in the electrical and computer engineering and mechanical engineering departments. So something about Maegan, she earned her Bachelor of Science in Mechanical Engineering from Georgia Tech, and then a Master of Science and PhD from Caltech. Then she also spent time as a postdoc at Caltech and as a research engineer at Walt Disney Imagineering, which is amazing. It's very cool. Every time I meet somebody from Walt Disney company, it's great. So Maegan's research focuses on hybrid system theory, robotic bipedal locomotion, human-robot interaction, and the biomechanics of lower limb assistive technology. And I think we get a sense of that from this very cool initial video. And her work really aims to develop personalized assistive devices to improve mobility for individuals with locomotor impairments. For her work, as you have seen in the bio, she has obtained a number of awards, which is great. And today we are going to hear more about it in their talk titled Integrated Humans into Our Humanoid Robots. I'm personally very excited to hear more about this topic, also about all the decision-making architectures that you need to design to be able to successfully deploy these systems. And therefore, I give you the stage, Maegan.
Thank you. Thank you so much for having me. So yeah, feel free to interrupt me at any point if you have any questions. I tried to pack a lot in here. So I think I'm going to do mostly a high-level kind of overview of how I'm thinking about this integration of humans into our robotic systems. But if you have any questions, yeah, feel free to stop me. So yeah, my name is Maegan. I just joined Georgia Tech about a year ago. So we're still a young lab, just getting going. And it's called the Dynamic Mobility Lab, or Dynamo for short. Okay, so I wanted to start with this video because, we've really been seeing, or several videos, we've really been seeing kind of an explosion in this field in the past year. So with the exception of the Asimo video, which is just demonstrating, so the top left corner is the Asimo robot, showing that there has been a smaller community thinking about this problem for quite a long time. So this was one of the earliest demonstrations of walking, but we've really come a long way since then. So the rest of these 5 videos are about a year old at this point. So this is kind of a year-old slide, and I'll have the next newest videos from only a few weeks ago on the later slide. But really about a year ago, we saw this explosion in terms of the realization that we're pretty close when it comes to being able to control robots for walking, get them out in the real world, and actually start solving this problem of locomotion. And so some of the major players here that you'll see, so Figure, of course, is one of the major players in this game. Digit, both Cassie and Digit, those are major platforms that you've probably seen. Apptronic has their own humanoid robot, and then of course Unitree. TeslaBot also has their own robot too. Okay, so these videos are only 3 to 1 week ago. So I'm going to do oldest first, which is only 3 weeks ago. But really the emphasis here is that this is incredibly fast moving, incredibly exciting time for this technology. So you guys being based in Boston, I'm sure you've seen the latest Boston Dynamics videos. And importantly, I've heard that this was only took them about 6 hours to get this policy. And so everybody seems to be doing the same pipeline, which is massively parallelized simulation in either Majoka or Isaac Sim. And then you learn kind of the reactions that it would take for all of the sensor data in order to stay upright in the real world. And I think really that what's been responsible for the recent progress that we've made is also integrating human motion capture data into these policies. So that's Boston Dynamics. This one is from Figure only 2 weeks ago. What I really like is this comparison video where you can see their multi-contact, what we call behavior, or foot rolling behavior, which gives you a much more natural stride pattern. And then of course, just a week ago, I think this was last Thursday, so less than a week ago, Unitree released this boxing video, which to me is very impressive because they're staying upright despite these discrete impact events that aren't entirely predictable. So I think this is all very exciting. And then the specific application that I'm excited about is how do we take this progress and how do we take this knowledge and control and actually apply it to systems that have humans in them. So in the middle, this was and still is, for the most part, state-of-the-art lower limb exoskeleton for people with motor paraplegia, which you can see the use of these arm crutches. So until we had the ability to control for locomotion, you had to rely on offloading all of the human's weight, and then the exoskeleton just plays kind of forward this fixed gait pattern to move the feet forward, but nothing is dynamically stable, not even really statically stable. You're really relying on these arm crutches. So what I'm excited about is how do we take control for bipedal locomotion and take the application of these lower limb exoskeletons for people who have motor complete paraplegia and achieve what's on the right, which is self-balancing locomotion. So you can see there's no use of arm crutches, and all of the weight is being loaded as expected. Okay, so what are the challenges here? So this is kind of how I'm forming this talk specifically, is around these 3 challenges. And to me, these are the challenges that prevent us from being able to realize those videos that I showed in the beginning for systems that have humans in them. And so the first one is that when we have a human in the system model is constantly changing and it is uncertain. So every time you have a new patient, that's a new model all of a sudden. Also, every time that, day to day, the same model, their model is probably changing day to day. So what this means is that the control that we're implementing on these devices needs to be robust to this model uncertainty. And so I'll talk a little bit about how I've been thinking about robustness, kind of some controls tools that we can apply to understand what makes a walking system either robust or not robust. But also something that I'm very kind of aware of and concerned about is that the sim to real transfer for these methods that are working in order to get these very impressive results on the videos that you showed earlier, the sim to real transfer is going to be extremely challenging when we have human subjects. So I think that's a immediate problem that we're going to have to solve in the near future. But so far, really, the research that I've been doing has been concerned about this. How do we get robustness in our offline control policies? Okay. The second challenge is that when you have a human inside of your device, they have feelings and emotions about how the device is moving. So unlike a robot that you can just tell it to do something and it's not going to necessarily complain, like a human passenger has feelings about what's happening. And so we have to account for those. And so my approach to this is that we can personalize the types of motions based on preference. So we call this preference-based learning. But we're also kind of going more into, can we use just learning from human feedback? That's kind of the area at large. Okay, and then the third challenge is that humans have physiology, right? We have to make sure that what we're doing is actually rehabilitatively beneficial for a human, that we're loading the body in the normal way, we're activating the right muscles, we're not causing any undue strain. And so kind of this summary is that these motions need to induce healthy kinematics and kinetics on the human body. Okay. So I think these 3 challenges can be broken up into these 3 areas of research. So one is just control for bipedal locomotion. How do we achieve better methods of control? How do we make sure that these methods of control are robust to uncertain models? The second complete area is this idea of learning from human feedback. So that's kind of going to be my 2 main focuses for this talk. Is the first half will be on the control, the second half will be on the preference-based learning. But another one that I think is really exciting and we're hoping to get more into moving forward is studying the human biomechanics and understanding when we develop these control strategies, what is it actually doing to the human body? But that won't really be a focus of this talk. But if you have questions, happy to talk about it. Okay, so the specific device that all of my research has been based around, and quite honestly, I think the most capable exoskeleton device out there right now is this Wondercraft lower limb exoskeleton called Atalante. So this device is designed and built by the company Wondercraft. They're based out of Paris, but they actually have an office in the US now in New York. They relatively recently got FDA approval. So this device now has FDA approval. And so in the robotics context, so on the right, you can think of this as an 18 degree of freedom robot. So it has 6 degrees of freedom in the floating base frame, and then it has 12 degrees of actuation. So it has 3 motors on each hip, 1 in each knee, and then 2 in each ankle. So you get fully actuated motion of the lower limb, and then We do assume that the patient's torso is fixed to the exoskeleton torso, and that's done through these kind of waist strap. Future work could be on actually treating these two kind of torsos separately, but we're going to assume that they're fixed together. Okay, so kind of just a note that I wanted to make. You guys might have seen this video. So this is Kevin. He's the main kind of pilot or test subject that tries all of these new controllers for Wondercraft. And then this video is actually taken in Paris at the Olympics, where he was able to carry the Olympic torch. So that was kind of a cool moment to see. And then another lesser known fact is that one of the co-founders of this company, his brother, is a patient with motor complete paraplegia. So there's a lot of heart in this company. I've been working closely with this company for about the past 10 years. So if anybody's interested in exoskeleton locomotion, highly recommend buying one of these Atalante lower limb exoskeletons. Okay, so on top of just being cool, there are some rehabilitative benefits of using these devices. So I'm just gonna pop a few on the screen. We still need more research about how these would apply to this self-balancing locomotion, self-balancing exoskeleton over flat ground walking. But these benefits were shown in this Locomat exoskeleton, which is bound to a treadmill. But it included things like increased blood circulation, increased bone density, improved cardiorespiratory function, decreased pain and spasticity, improved intestinal functions. And then there's a few, but not really well shown, expected results that include actually benefits towards recovering locomotion on your own. And then part of what's exciting about the self-balancing is that they've shown that the arm movement is actually important for this recovery after spinal cord injury. So these are kind of some of the motivations behind why we're trying to do this. And then there's also just the human factor. So I think it gives patients a lot of confidence to be able to walk again and get out of their wheelchair. Okay, another note that I would like to make is there are multiple different types of exoskeletons, right? So you guys might have heard about research being done for what I would call an augmentative robot, a robot exoskeleton for augmentation. These are designed for people who have full motor capabilities. So I'm not, my methods of control aren't applicable towards these robots, but these are different types of exoskeletons. There's also exoskeletons purely for the purpose of rehabilitation. So these are ones that are bound to a treadmill, they're bound to overhead support. Really the control that we've been targeting is focused on this rightmost category of exoskeletons for restoring locomotion. So we want them to be able to get out in the real world and actually recover this locomotive ability for people with complete motor paraplegia. Okay, so this is our approach. So you'll see it's quite general. I think I'll talk about some places where you can plug in different methods. But in general, the first step is you have to fuse the exo and the patient model into what we're calling a human exoskeleton model. So how we do this is we actually take 4 measurements from a human patient: their total height, their total mass, the length of their shin, and the length of their thigh. And the importance there is that you need the ankle joint, the knee joint, and the hip joints to match between the two exoskeleton and the human. But once you have that, we really fuse the rest of the inertial properties. The rest of the human's inertial properties we extrapolate from anthropomorphic data, and then we fuse those two and we get this patient-specific human exoskeleton model. So this is really what I mean when I say we have a unique and changing model for every single patient. We take that model and we can plan motions for that specific model. And so I'll talk about it a little bit, but we're going to use something called hybrid aerodynamics. It's a method of offline trajectory generation, but you can really think of this as any motion planner. And so I'll talk a little bit too about the benefits of it being an offline motion planner, but it could be an online motion planner too. What's nice about that is you can feed in desired gait features. So you can feed in a desired speed, desired step length, desired step width, desired step height, maybe any kind of motion specific parameters that you're wanting to match for patient comfort. Once we have those motions, we're just going to feed them to some sort of a tracking controller. At the simplest level, we just do PD tracking, but we've tried more complicated methods of tracking too. You could plug in something like reinforcement learning here in order to track these offline motions in this case of disturbances. How do you replan? But at the simplest level, we just do PD tracking, and then you feed these torque commands to the actual exoskeleton robot. So that's the setup. Any questions about the setup? I'll pause for a second. Okay, then I'll keep going. So yeah, like I said, I actually am a big fan of offline gait generation. I think this is a point of contention with some of my peers. And I think replanning is really important, but I think there's some important benefits of generating these motions offline. One is that they're predictable. So if we have predictable references, we know that the exoskeleton is not going to do anything unsafe or undesirable. And at least we have a close reference of something that we want to follow. I think this is actually pretty similar to using like offline collected motion capture data. It's just these offline gait references are actually already model specific for the robot itself too. So they take into account joint limits, actuation limits, and then they give us some close goal that we're trying to track. So I like them. I think they're predictable. The fact that we're solving these offline optimization problems means that we can actually encode hard constraints into our problems, like I mentioned, actuation constraints, joint limits. I think another benefit is that they're intuitive to tune, right? So we actually know what all of the constraints are. We know what our cost function is. And I think that that gives us a lot of very intuitive tuning parameters. I think that it's gotten pretty fast to generate these gaits. So for the exoskeleton, if we code gen it into C++, it can take 30 seconds to get a gait. It's really not that long to obtain these references. And yeah, like I mentioned, they can be used as an offline reference for other methods like reinforcement learning, model-based control, whatever you would like. Okay, so we use the specific method of hybrid zero dynamics. I'm just gonna kind of give an overview and then we'll talk about ways that it can be improved. But the heart of our method is that we model walking as this hybrid system, right? So you can model the continuous swing phase in this continuous domain, and then the discrete impacts as this edge. By modeling it this way, we actually have theoretical guarantees of stability. You can encode then the actual trajectory optimization problem as just a nonlinear program. There is this nice toolbox called Frost that helps encode these using iPopt. I don't know why I had automatic transitions. I want the video. Okay. And then when you solve these optimization problems, theoretically, according to the math, it gives you these gaits that are provably stable. At least that's what you would expect, right? The reality is that while they are all theoretically stable, some are more robust to model uncertainties than others. So these are all three gaits that were generated using this offline method of gait generation. But you can see the one on the right gives us stable locomotion, while the one on the left and kind of the one in the middle are not actually stable. So this is really what sparked a lot of the questions about these motions being robust is even just in this offline trajectory generation framework, how can we actually mathematically encode robustness so that every gait that we generate is robust to modeling uncertainties, is robust to these differences in patient models, changing patient models. Yeah, we don't want to have to do this tuning process by hand. Of course, you can do this tuning process by hand. It's just we add what I like to call essential constraints. So these are things like things on the step length, things on the step duration. And by kind of fiddling with these parameters, you can shape the gait to be something that is robust. So yeah, these are the examples. Kind of the takeaway is that certain gaits yield stable and robust locomotion, right? So this method of offline gait generation, it is pretty powerful, pretty fast, gives us these predictable motions. And as long as we've tuned these constraints properly, it gives us stable locomotion. And so, yeah, the goal is to mathematically describe this robustness in order to systematically generate only gaits that are robust. And so this slide is a little busy. I apologize. I'm trying to condense all of the information, but there's multiple ways that I've tried to think about this question of robustness. And so I don't think it's simple. I think there's many ways that we can answer this problem. I'm going to talk about these three methods, at least just show you some fun videos. I probably won't get too deep into the details. But if you would like to know more about it, just ask me and I can let you know. the first one is kind of accounting for just impact uncertainty. So how can we make these gaits more robust through the discrete impact events? The second one is trying to get provable guarantees of stability. So can we actually come up with certificates that certain gaits will be able to handle changes in terrain? So we cast that as an input to state stability problem. I'll talk about that too. And then the third one is saying, okay, if all we care about is just that the walking stays stable, how can we use sampling to our benefit and massively parallelize simulations and just come up with gaits that can handle a larger set of disturbances? So these are kind of three different techniques. I think they all have pros and cons. And so we'll actually compare the pros and cons at the end, but I just want to show you some fun videos. Okay, so like I said, the first one is just thinking about impact uncertainty. And the real simple approach is to use something called saltation matrices. So we took kind of a simple idea, which is to say we can calculate the matrix norm of this saltation matrix. And there's a really great survey paper on saltation matrices. That's the thing shown at the bottom of the screen by Aaron Johnson's lab. Okay, I didn't mean to do that. But if you would like to know about saltation matrices more, I think that survey paper is really wonderful. As a whole, what it's doing is it's measuring the kind of sensitivity through these impact events. And so by minimizing the matrix norm, we're trying to minimize the amount of errors that will propagate through these impact events. So this was our setup. We generated 3 different gaits. Apparently all of my slide transitions are on, which I really didn't mean to do. We generated 3 different gaits. One of them only had minimized the energy that it takes into the cost function. So we're going to call that the energy efficient gait. One of them only tried to minimize the saltation norm. So we call that the robustness only gait. And then one of them had both of these terms in the cost function. So we're both trying to minimize energy, and we're also trying to minimize kind of sensitivity to these impact uncertainties. So these were the 3 gaits that we generated. This is when we put them on hardware. So I think this video is more interesting. But you can see that neither the energy efficiency only or the robustness only gaits work very well. So the takeaway here is that I think it's important to account for robustness, but it's not the only thing that's important, right? Maybe that's intuitive, but this gait in the middle works. This is on the Atalante exoskeleton, and I mostly like to include this video just to prove that the exoskeleton is the thing responsible of walking. It is not the human inside of the exoskeleton that's responsible for the locomotion. This is a full biped device. It's capable of walking by itself. But again, you can see that the gait in the middle is able to be stable on its own. The other 2 are not. Maybe one thing that's important to note is this is all just open loop PD control. So it really shouldn't be stable on its own, but just through robustness, it's able to walk independently. Okay, that's the first method. The unsatisfying thing about it is that we don't have any guarantees of how robust it is. So that was the motivation for the second work, which is saying, what would it take to get provable guarantees? What we do is we cast this as an input to state stability problem. So really the question is, does there exist a set on the switching surface, which for us is when the foot impacts the ground? We're going to only look at the states when the foot has impacted the ground, and we're going to ask, does there exist a bounded set that scales with respect to how much the terrain height is changing? And so it turns out, yes, it requires quite a lot of math in the sense of making sure that this point Carré return map, or your step-to-step dynamics, making sure that this is complete, that this function is complete. That's kind of the challenge here. But what we can get at the end of the day is a theorem that actually proves that there will exist this bounded set if you can show through a robust Lyapunov function that you have this input to state stability property. So I know this was kind of a lot. The takeaway that I want is that we can come up with theoretical guarantees. And so we can solve for these theoretical guarantees iteratively by growing the size of our initial condition until we find a set that is input to state stable. And so we compared 2 different gaits. One gait that we wouldn't expect to be robust. This is kind of something called like foot shuffling. So we wouldn't expect this gait to be very robust. This one we would expect to be much more robust. And when we run it through all of this kind of theory, we get that this first gait is not what we were calling delta robust, where delta is the change in the step height. It's not robust to any changes in step height, as opposed to the second gait is provably stable for changes up to 6 millimeters. Now, we were a bit surprised. This isn't very much, right? This is a pretty small change in step height, but it's the worst case found. So what we're saying is that you can have continuous upstair motions of 6 height or continuous downstair motions of 6 millimeters, and you will remain stable. Now, this isn't very realistic, so we extended it to something we call ISS improbability. And really the key difference here is that we plugged in an expectation for satisfying this robustly optimal condition. And so now we get a lot more kind of realistic guarantees. Of course, these are probabilistic guarantees now, they're not certifiable guarantees. So this first gait went from 0 to 5 millimeters, and the second gait went from a guarantee of 6 millimeters to a guarantee of actually 30 millimeters or 3 centimeter step heights. So this was pretty exciting. The downside is this is a computationally expensive algorithm to run. It took about 4 hours to certify. And granted, I didn't do much code optimization, so it could be faster, but it took about 4 hours to come up with these certificates for each gait. So not very practical. So that kind of really motivated this third idea, which is saying what we really are looking for are sets that are invariant, right? So let's just take a initial set. Let's sample that set and let's propagate all of those samples forward by 1 step. And then let's look at the largest ball such that those samples returned into the initial set. So I have a diagram of this in a second, but really we're casting robustness now as a set invariance problem. Okay, and so we'll do it in this order. So what this looks like is, this is what I was talking about. We're just thinking about perturbations in terms of the yaw velocity, the pitch velocity, and the roll velocity. So these are the angular velocities of the torso. We're going to take small perturbations away from our fixed gait, the fixed point in our periodic orbit, and we're going to individually simulate one gait in parallel for each of these perturbations. What this leaves us with is a Poincare return map for a single return of where all of these perturbations would land on the same surface. And so this is our initial set of disturbances. We simulate all of them forward by 1 step. This is showing massively parallelized. Well, okay, we're showing it in series, but these are all of the going forward in 1 step, and that leaves you with after 1 step where everything returned. Okay. Then you can run an optimization problem to find the largest ball such that after 1 step, the points return within that ball. So I'm probably not explaining this the best that I could. We cast this as a discrete time control barrier function condition, just because it kind of gives us some nice smoothness properties, but this is just a set inclusion condition. And so the problem is that the number of points that you're considering change with the size of the ball. So we're only considering the points inside of the radius r. So like for this ball, what we do is we take all of the green points, all of those green points are within this optimum size of radius r star. And for all of these points, the return points also remained within the ball. So we're trying to find the largest radius such that this condition is true. If this condition is true, we've certified, again, stochastically, this isn't really a certificate because we're not doing this in a continuous space, we're doing this through sampling. But we've certified that everything within this ball will return to within this ball. I don't know if this is confusing. Hopefully it's not too confusing. Okay. Now what we can do is we can embed this optimization problem inside of a larger optimization problem to actually change the gaits and synthesize new gaits in order to optimize for the size of this ball. So we want the largest set of forward invariants. And so this is what the results ended up giving us. So on the left is a gait where we did this optimization problem, but we just optimized for the number of steps. So this is our comparison. What happens if you just took robustness as simply the number of steps that you can take, and we optimized a gait, versus this one's actually optimizing for this robustness metric. And you can see that the gait on the right performed more robustly, performed better on a hardware. So we're calling that robust. We said, okay, this works pretty well. What if we extend it to multi-contact walking, or this foot rolling behavior? And so we did that too. And we were pretty happy with the results. We were able to get this foot rolling behavior just through open loop tracking of our offline references. So we were pretty happy with that. Okay. So pros and cons of all the methods. I think the first one of accounting for impact uncertainty, this is a very practical metric. It's not very intuitive in terms of thinking about this sensitivity. It doesn't have intuitive bounds on what you're able to handle. It's just this matrix norm at the end of the day. And there's no theoretical guarantees associated with it, but it gave us some pretty good gaits, and it was very practical. I think the theoretical guarantees through input to state stability, the benefit here is that you actually have these formal guarantees of which gaits are able to handle ranges of step heights. I think this is an intuitive metric for robustness, but it's not at least yet practical. It takes about 4 hours per gait, so we can't embed this into a synthesis problem. The last method that we talked about, I think this is a good middle ground. I think it's moderately intuitive, but it's only moderately expensive to run. It's not as practical as the saltation matrices, but I think it's more practical than kind of the theoretical guarantees. So we're still exploring other ideas too. I don't think that we've entirely cracked the code on how to mathematically guarantee robustness or think about robustness, but this has been the work that we've been doing so far. Okay, so with the remaining...
Question. May I ask a question? Quick question.
Yeah,
so
please.
in the third method, you still have to solve that optimization at each time step, right? To get our
but it's very fast. Yeah.
Okay. So it's still an online kind of method, and then you still call it like fast, because like solving that optimization at each time step, doesn't it make it like computationally like expensive again?
No, so I guess we're solving it in the loop of the synthesis problem. So when we're trying to synthesize these offline references, between every time that we synthesize a gait, we're going to check this measure. We're not doing it directly in. So this, I think this is a key difference, and I'm glad you asked this question. For the saltation matrices, these are fast enough that we can actually embed it directly into the optimization problem of the trajectory optimization problem. On the right, this is done iteratively between gait designs. Here we go. I went way too far. Okay, this is what I'm trying to get to. We did a Bayesian approach to optimizing the gait. So we're not actually running this optimization problem inside the trajectory optimization problem, but we're going to run it between trajectory optimization problems.
I see. Okay.
So
thank you
it's faster than 4 hours, which allows us to do this Bayesian optimization approach, but it's not fast enough to be embedded inside of the actual trajectory optimization problem.
Okay, great.
Yeah,
thank you so much.
Yeah, no problem. That was a good question. Okay, so I've kind of run out of time to talk too much about addressing user comfort, but we can talk a little bit at a high level, which is just, once we come up with these motions, we still have to account for user preference in some way. And so we recently wrote this kind of survey paper on all of the different ways that people are thinking about accounting for user comfort and thinking about accounting for preference in these human kind of robotic applications. The most common method is definitely self-exploration. So you create a large explorable space of possible parameters, and then you actually allow the person using the device to explore the space themselves. So one of the most common approaches is you have a tablet with a touch screen, and the patient can actually press different places on the tablet, and it'll change the behavior of the device that they're wearing. This is common for like ankle exoskeletons or ankle prostheses where there's only 2 parameters, right? Because you can make this nice grid, they can search the space themselves, and they can find parameters that they want. The problem is this becomes harder to do for larger action spaces. So patients can't really keep track of all of the changes that they're making. And so I think there's some work that can be done in terms of how do we do this for higher dimensional action spaces, but I think it becomes more challenging. In an ideal world, this another technique is, well, if we had a model for user comfort, we could just directly provide gaits that already optimize for comfort. The problem here is that we don't have this existing model yet. So ideally, someday we'll have a model for which exoskeleton gaits are more comfortable than others, and then we'll only provide users with a low dimensional space of at least comfortable gaits. We don't have that. And so instead what we do is we just learn from human feedback. We're going to give people options, we're going to ask them for feedback, and we're just going to learn directly from the feedback that they're giving us. The two approaches for this, there's batched supervised learning, which is when you give them a whole bunch of gaits, you collect a whole bunch of data, and then you learn from that data. The problem is that that's not as data efficient as if we did the one on the right, which is this interactive learning. So you only give them one gait, you collect one bit of information, you update your model, and then you give them another gait. The benefit here is that it requires a lot less data to get to a good action. So we're not going to force the user to go through all of these bad behaviors just to collect data. We're actually going to give them a limited number of gaits until we get to something that's good. So this is the high level kind of architecture that we've developed over time. And so let's start over with the gait libraries. Basically, what we do is we can parameterize different gaits through these features. So a two-dimensional example would be just step length and step cadence or step duration. That gives us a gait. We let the person try it. And then let's say that they had tried one in the past too, that we now ask them, which gait did you prefer, this one or the last one? That gives us a pairwise preference. We also ask them, do you have any suggestions? Is there something you think you would like? This also gives us a preference that we downweight because they haven't actually tried that other gait. So for instance, they could say, I think I want a longer step length. And then we could give that as a synthetic preference. And then they can also give us an ordered label or an ordinal label by saying something like, this gait was bad, this gait was good, this gait was terrible, right? We actually have rankings that we can obtain automatically. So then we can take this feedback and we can actually model our belief of their underlying utility function based on this preference information. We do this using a GP. We model their underlying utility as a GP. And then from this GP, we can sample based on if we want to find the best gait as quickly as possible, or if we want to actually learn what their utility function is. There's different ways of sampling new actions, but that would then give us a new action and we could continue. So this is kind of what the process looks like. Again, this is Kevin. This is the same test pilot that we've been working with. And so this would be an example of the least preferred gait, something that made him feel uncomfortable. So we did about 40 iterations. So we gave him 40 different gaits. This is now the results after we did it. This was what we discovered to be an average, a median preferred gait. So he's able to walk, but you can see he's really having to watch his feet in order to know how to shift his weight during the locomotion because it's not very stable. And then this would be a most preferred gait. So this was something he felt comfortable in. He was able to use the turning feature because the gait was stable enough to do so. So this optimized for his preference. Okay, what we found is this is applicable for any application that relies on user intuition. So it's really nice as you can really optimize any set of parameters just based on human feedback. So we did this with the spring foot amber robot, and you can see that we didn't account for the springs mathematically. We just generated gaits for a point foot model, and then we put them on a model with a spring. And we said, can we actually systematically find a gait that optimizes for a operator looking at the gait and giving us preferences? And so we did this. This also took, I think, about 30 iterations to find a good gait until we got to this gait that you see on the right. And so we were surprised that we were actually able to get very good behavior just through systematically searching this parameter space using human preferences. Okay, so we did open source the toolbox if you want to play around with preferences. It's just an archive paper, but we did our best to kind of document the toolbox. It is in MATLAB. We're working on a Python version at the moment. If anybody would like to help develop a Python version, we are, of course, more than happy to chat. Okay, I think there's a few exciting avenues to continue this preference work. One is thinking about multi-objective preferences. So we have a paper on this that just got accepted, so it should be coming out soon, which is thinking about what if both the clinician and the user had a preference? How could you actually simultaneously optimize for two different preferences? And then the other one is, if we want to think about this offline or this self-exploration, how can we create these diverse policy libraries that a patient can go in and explore themselves? Okay, so that's the conclusion. So I think it's really important to think about both robustness and personalization when we're translating these techniques from bipedal locomotion to lower limb assistive devices. Some just additional 4 open problems. One, how do we think about variable assistance? So I think this is going to need more improved control strategies. So you can see in the video that the clinician's really having to hold the exoskeleton during this variable assistance strategy. That's because the stability degrades as you relinquish control to allow the patient inside of it to use more of their own muscle effort. The second one is, how do we get more dynamic behaviors like going downstairs? This is a video that Wondercraft put out, and I always, notice that they kind of strategically have somebody standing right next to it as it's walking downstairs. And so I think this is just because it's a very fragile maneuver to do, walking downstairs. It's very dynamic. You need to catch yourself. And so I think there's more work that could be done in terms of getting these other types of behaviors. One that I'm excited about is, how do we understand user preferences? What does it mean for a gait to be comfortable, not comfortable? I think this is just going to really require more data collection. And then, of course, how do we think about the biomechanics, human muscle effort, human biomechanics as we're doing these control strategies? Cool. Okay, so thank you for listening. Hopefully there's some questions. If you want to look at any of this work yourself, here's a link to my Google Scholar where you can find most of the publications. And then this is our lab website if you're interested.
Thanks so much, Maegan. Very nice talk.
Thank you.
A lot of stuff, actually. So let's open the stage
maybe
for
too much.
questions. No. I mean, it was meant as a compliment. So you can either write in the chat or ask directly, or maybe do the icebreaker. So, well, I start by the end. I have to say I'm quite intrigued by this multiple preferences perspective.
Yeah.
I got to know this last week because I'm writing a proposal with Aaron, and he sent me the paper, super excited about it. But do you want to expand more on that?
Yeah, totally. So when you go to multiple preferences, you start getting into a multi-objective landscape, right? So, I think if we assume that the preferences can be aggregated into a single preference model, then it's not that complicated, right? Because if you can aggregate these preferences, then you basically are just getting twice as much information and you're trying to learn the same shared landscape. I think the complicated part comes in the hypothesis that these preferences could actually be conflicting, right? So I think the best example of this is just every time you have to go and see a physical therapist, the physical therapist might ask you to do something that's uncomfortable because it will be like health-wise beneficial for you. So in that moment, you might have a different preference than the one that your clinician is giving you. And so if those preferences are conflicting, now all of a sudden you have this Pareto frontier or this multi-objective optimality. And so at least this paper was really trying to target, how do we think about learning where these Pareto frontiers lie just from pairwise preferences, and then casting that as an active sampling problem. So we kind of took the tools of preference-based learning and multi-objective optimization. And really the key was thinking about it in terms of this sampling for learning this multi-objective front. So we use what's something called Chebyshev scalarizations, which it's a traditional way of kind of breaking apart a multi-objective problem into multiple single objective problems. And so then you were just doing the same type of Thompson sampling. It's one of the active learning strategies where you're trying to find the best actions as quickly as possible. And we just do it using these Chebyshev scalarizations.
Nice. And in the future, you imagine people filling forms where they're asked to choose between one option and the other, and based on this, you form some preference structure, or what's the use case you imagine? Yeah,
totally. So what we'd like at the end of the day, and part of this, So what we would really love is to eventually be able to also leverage the power of LLMs, that they don't have to fill in a form, they just talk. And then the job of the LLM is to translate that into preferences. So hopefully we can get away from forms, but for now it can be a form. So you could imagine like a tablet with different sliders where as you're giving them new kind of suggestions, right? Maybe you'll like this. And then maybe you have a slider that's saying, how much did you prefer this one? And if you slide it all the way to the right, it's I preferred it much more. I preferred the new action much more. If you slide it all the way to the left, maybe it's I preferred the old action much more. And then you can collect this feedback. And maybe there's two sliders, one's for the patient, one's for the clinician. And maybe this tool is now something that the clinicians use in the clinic in order to help find these behaviors that are both beneficial in their eyes, but also comfortable for the patient. I do think, okay, much into the future, once we have enough of this data, I would love to be able to actually extrapolate kind of the mapping between different patients, maybe different features of the patients, and better predictions of what we think they'll like automatically. So ideally somebody comes in and just based on how they're answering the first few preferences, we can say, oh, okay, from all of this other data that we've already collected, we have predictions of what we think you'll like. I think the problem is knowing how to parameterize people, right? Like, how do you think about how to group them into different preference characteristics, right? Like, is it their experience level that matters? Is it kind of fundamental to their like adventurous personality characteristics, right? Like whether someone wants a more dynamic but potentially less it's not that it's less safe, but it feels less secure versus somebody who might want a much slower, more secure feeling gait. So the problem is, we don't really have any good ways of guessing how to parameterize people into these different categories. So we want to just ask them for feedback, learn from feedback. But I do think we can jumpstart our predictions a lot better once we have better data.
Okay, that's super interesting. It's I will send you a couple of it connects to preferences in drivers. I am more on the on another application, but it's very interesting perspective.
Yeah, totally. It's very well connected to preferences with driving. Totally.
Nice. Any other question for Maegan from the audience? It's quite a silent audience today, so I guess it's it was a very good talk. So maybe the other thing I wonder about is how do you, so here you're dealing with, at the beginning of the talk, you had a very nice slide with all the architectural decisions, essentially, and also the feedbacks between the various architectures. How do you deal with, for instance, limited computation, where you have to approximate these models, for instance, with reduced order models and these kind of things?
Yes.
Do you have any future work on this? Stress testing, essentially the computation limits.
Yeah. So is this the slide you were talking about too, by the way?
Yeah, exactly. This is a nice one.
Yeah, so it's interesting with reduced order models. So I think reduced order models are popular because they're much faster kind of techniques for coming up with these planning tools. To me, the question is really, when are these reduced order models accurate? So that's the question that we're trying to answer right now, is coming up with conditions under which certain reduced order models are appropriate versus maybe you need a higher fidelity reduced order model. For instance, the exoskeleton has extremely heavy legs. So I think that the inverted pendulum model is actually not a good model for the exoskeleton because you're not accounting for the inertial effects of these legs. So, but we don't have really a good way to prove that other than you try it and it doesn't work that well, right? So I think a lot of people seem to be thinking about this question. So maybe somebody else will solve it for us and then we can just use the results. But I guess that's something that I'm more concerned about over the speed of kind of these different methods. But yeah, I mean, like you were saying, you could plug in a lot of different planning algorithms in this trajectory part, right? So you could put in MPC, you could put in reduced order model motion planning, and then the tracking controller would now be, how do you track those reduced order models?
Yeah, exactly.
Yeah. There's a ton of different tools that you can use. I think, for our specific system, reduced order models aren't really appropriate because we have such heavy legs. So we haven't been doing a ton of work there. And then MPC is very model specific. So you're planning actually based on your information from the model. And so we would rather have references that are based on the model, and then our actual tracking controller not be based on the model. So I think there's just like domain specific decisions that get made.
Okay.
But in terms of
Thanks
the
so much.
speed, no, I'm not too concerned about speed for any
Okay.
of these.
Okay.
Yeah.
Thanks so much. This is great. I don't see any question from the chat. I think you had on your last slide, though, if we can pull up the QR codes again, I think people can reach
Yeah.
out in case they have deeper questions.
Yeah, let me find. Why can I not?
And I just booked you again for another seminar at this this
Perfect.
CDC. Yes.
Oh yeah. We can chat more about the newer stuff. Yeah, there's a lot of exciting work in this space. I mean, it's moving so fast, so maybe we'll have new results. I think the one thing that we're trying to show now is the extent to which these robust offline gaits would actually improve reinforcement learning. Since that seems to be the tool that everybody's gravitating to, I think it's very powerful for real world robots, because it's basically learning how to handle all of this uncertainty in kind of a structured way. But that's something that we're thinking about very actively. So maybe those will be the results that we can talk about for the next one.
Very nice. Very nice.
Yeah.
Well, thanks so much again, Maegan, for the great talk. Good luck for the next steps. And thanks
Thank
everyone
you.
for joining.
Yeah, thanks for having me.
All right.
Bye.
Take care. Bye-bye.